going to review drying compounds, shape, and hopefully a little bit of IMF. When drying your compounds, one key thing to always do is to add up all the valence electrons so that you don't miss out on anything. For example, especially if you have resonance or if you have ions. So one structure we've looked at quite a bit this year is ozone. 3 times 6 is 18 valence electrons, always the first thing you want to do. They'll probably give you some information about the O's, but in drawing this, make sure that you have complete octets on terminal atoms and then finish out on a central atom. And recall that elements in period 2 do not have the ability to expand their octets.
For resonance or atom, it's just the opposite, right?
You got it. So this one has resonance, which you would want to illustrate. And again, 2, 4, 6, 8, 10, 12, 14, 16, 18 valence electrons. Make sure you check that. It's especially important, for example, if you had a triiodide ion, 3 times 7 plus 1 for the additional electron is 22 valence electrons. And here's where you might miss something if you did not count your electrons. In most cases, the halogens are going to form single bonds. So don't double them unless you absolutely have to. Complete the octet on the terminal atoms, and you now have 6, 12, 14, 16, 18, 20, 22.
That's linear, right?
And that is a funny linear one. You have 2 bonds, 3 lone pairs. So the electron group geometry here, you have 5 electron groups. So the electron group geometry is trigonal bipyramidal. But the molecular geometry, which is typically what they're going to ask you, is in fact linear. And I was sloppy here because in drawing this, whenever you have an ion, you of course bracket and put a charge there. Don't forget, if you have an ion, put it in brackets with the charge. And there are several things that we can point out here on this question.
If you have ammonium ion, would you only have 4 valence electrons that you're looking for?
If you had ammonium ion, you'd have 5 plus 4 times 1 minus 1, because of the positive charge, is 8 valence electrons. And that would give rise, and again, when you draw this, don't forget, if you have an ion, to put it in brackets with a positive charge on it, 2, 4, 6, 8.
No, I was just referring to the nitrogen, so you would minus the 1 from the plus 1 charge, right?
Absolutely. Would that be such a neutral? Yes. And keep in mind, when you're dealing with polar, nonpolar, if you have ionic substances, they're ionic. They're not polar or nonpolar. And that's come up in the past as well. For example, if you had a triiodide ion, which is purple, it would dissolve in water, forming ion-dipole interactions. So be careful there.
On Khan Academy, there was a drawing example on the one that we use for Le Chatelier's principle, the COCO one. And he said it had resonance, but it didn't look like it did.
COCl2, phosgene.
What's the one we use for the pink and blue?
That's very complex because it depends on which species it was and whether it was a complex ion. So that might be more than you would need to know. Okay, so just in regard to drying, make sure you count all the electrons. That's important. If you have an ion, don't forget the charge. If you have resonance, indicate both. And you're probably not going to get one that's terribly difficult. And they're very big on the Ku group lately. And golly, I think I would pray for anything in regard to a Ku group. You've seen it to death.
But they accept a skeletal structure.
Yeah. You're talking about, I wouldn't go there. I would not do that. So with your drawing, again, count them, place, be very careful. Only expand an octet if it's in period 3 or higher. So neither oxygen nor nitrogen can expand the octet. Also be careful with nitrogen. If you get an odd number of valence electrons, you can have an incomplete octet on the central atom, not a terminal. So here,
Be louder, please.
you have 6, 8, 10, 12, 14, 16, and you'll have a lone electron on nitrogen. Also, don't forget with your hybridization, I know I reviewed this in class the other day, you have 1, 2, 3 electron groups. 3 electron groups corresponds with sp2. 1 plus 2 is 3 electron groups if they ask about hybridization. So in this one, you have 1, 2, 3, 4 electron groups. So what would the hybridization be here? sp3.
The NO2 have resonance still?
It would. This could be single and double there.
Anytime that it has like 2 different bonds but that are bonded to the same element like that, does it always have resonance in that situation?
Most likely. I hate to say definitively because there'll be something weird, but yes, I would say yes.
Whatever they give us is most likely going to have resonance because that's what they want to assess, right?
Maybe, maybe not.
Which one would it wouldn't have resonance?
You just want a structure that doesn't exhibit resonance?
But that could feel like it might. Maybe.
Yeah.
No resonance there. That's the only thing you could draw. Something like this. No resonance. Why is this a polar covalent molecule? You've got a dipole right there. Difference in electronegativity there is substantial. Polar and nonpolar? Polar as well. Dipole right there. Polar covalent molecules have London dispersion forces and dipole to dipole moments or interactions. Why would this molecule be nonpolar covalent?
That's
Perfect
also
symmetry.
It exhibits perfect symmetry and therefore the dipoles cancel. So that's a nonpolar covalent molecule.
If you're the one drawing it, how can you be sure that it exhibits perfect symmetry?
when you have the same thing attached all around in a tetrahedral configuration, that will exhibit perfect symmetry.
Like if they're all halogens, they're not all chlorine. Don't they have the same dipole moment?
No, they wouldn't. Like if you had fluorine there, the dipoles wouldn't cancel. That dipole would be stronger than the others.
Oh, 'cause it,
And keep in mind, if you ever have one lone pair on the central atom, you're going to have a polar molecule. Bent is polar. Just be careful. There are a few shapes where you can get nonpolar with lone pairs. Square planar is one. The funky linear is one. And
the funky linear you showed us, that's just ionic, right?
that's ionic. The funky linear, the square planar, those are the two. And these shapes are all shown here. This is something you do want to look over. And don't worry about sigma bonds in this regard. You know the difference between a sigma and a pi. A single bond has sigma only. A pi has sigma and a pi. Or a double bond has a sigma and a pi. And a triple bond has... Okay.
Wait, it's 2 sigmas, 1 pi, right?
A dipole moment is when you have unequal electron distribution in the bond. So this is a dipole moment here where the oxygen has a partial negative, this has a partial positive, and the electrons are shared unequally, where oxygen pulls the electrons more toward itself than carbon, giving rise to a dipole moment. Unequal electron distribution in a bond. Not enough to make it an ion, though. So these are all your different shapes. Hybridization shown here. You don't need to know the D-related hybridization anymore, but you can look through that. In regard to the bond angles, again, you really want to be comfortable, I would say, with, this looks like it's a typo. This bond here, these aren't written that well here. This should be 107 here, and this should be 104.5. So be careful there. I almost feel like it got out of whack. Like this looks like I tried to type over, and I kind of feel like for some reason this slid. I don't know how that happened. So that looks a little bit better. It looks like something moved. Maybe I typed something in and something else moved. So be comfortable there, especially with the reasoning. Trigonal pyramidal structures have smaller bond angles than tetrahedral ones because the lone pair of electrons repels more than a bonding pair of electrons, thus compressing the bond angle.
I thought tetrahedral could have 90 as well.
No. 109.5. Don't do that. Careful. Don't do that. And then with your water molecules, for example, you've got two lone pairs of electrons. The lone pairs repel one another in addition to the lone pairs repelling more than the bonding electrons, hence further compression. Those they like to ask, so I'd be comfortable with it, and I've indicated that down here. This we've seen before. Here's your dipole moment, again showing this unequal electron distribution. Here's an example of resonance, and this is sulfur dioxide, which you have seen previously. Here's your triple bond with a sigma pi pi. And the other thing you want to be comfortable with, withdrawing bond energy. Again, you can calculate delta H. Make sure you do reactants minus products. Bond order you should be familiar with. Formal charge. In regard to formal charge, if we went over here, for example, nitrogen by itself has 5 valence electrons minus the 4 that are attached, if you will, is equal to +1, consistent with the charge.
Formal charge is only for central atom.
Nope, it can be for everything. So if you look at this one right here, this nitrogen, again, 5 minus 4 is +1. And on the oxygen, you'd have 6 minus 1, 2, 3, 4, 5, 6, 7 is -1. And you would expect oxygen to have the negative formal charge if you have to distribute, because it's more electronegative than the nitrogen. The one that I think is always really messy is carbon monoxide. It has a very unusual structure in that you have a lone pair on the carbon. Here you'd have 4 minus 5 for -1. Here you have 6 minus 5 for +1. That's unusual because oxygen's more electronegative and you wouldn't predict it as such, but that is carbon monoxide.
What would they ask you? They would literally just ask you.
They
on
could
the
ask you for
formal
formal charge in carbon monoxide. Carbon monoxide is a polar covalent molecule.
You didn't have a formal, overall formal charge, you see it.
Correct.
So formal charge, you subtract the number of bonds and lone pairs.
A lone pair counts as 2 electrons.
And a double bond is 2 and a triple bond is 3. Yeah, it's not like a square is this. So,
In regard to your,
and then you take the first number from the periodic table.
right. In regard to your different types of IMFs, I think you're comfortable here. All covalent compounds have LDFs. Non-polar have LDFs only. With your polar covalent molecules, you're going to have dipole to dipole, which is stronger than that of an LDF, but all of these IMFs are considerably weaker than covalent bonds. Be careful there. Some molecules have the ability to hydrogen bond. You have to have an H covalently attached to an N, F, or O, and then that H will hydrogen bond with an N, F, or O on a different molecule. You had a question. If you have a dipole to ion interaction, for example, let's say you have ions, here's calcium ion, here's chloride ion, and if this represents your water molecule, where that's the O and these are the H's, what you're looking at here, keep in mind partial negative versus partial positive. So Mickey would be positioned in this regard, Mickey would be positioned in that regard. An ion dipole is the interaction between the ion and the polar covalent molecule positioned properly. So that would be your ion dipole interaction. And they love asking you to draw these. Don't attach them. You've got a little bit of wiggle room, if you will.
When we do draw them, do we need to draw the little lines or just draw the circles?
It depends what they ask for. If they ask you to label it, I would draw the little lines there. And they usually ask for both, I'm
That'd be
thinking.
an explanation if they ask, as like a latter part of a.
I'm sorry, an explanation for what?
If they ask, like as one of the later parts, like a G of like a long question, if they ask why would calcium chloride be more would conduct better electricity in water, could you say it's because it has an ion dipole moment with water?
No. You would say that, I don't think so. With calcium chloride, you would indicate that in order for ionic substances to conduct electricity, the ions, the compound must be comprised of ions, and the ions must be able to move freely. So you're saying because the ion dipole interaction is stronger than the interionic interactions? Okay, yeah, then I see where you're going there.
So
Yeah.
that could be a lot of.
Yeah. And then this really just put everything into perspective for you. I want to take a look in regard to, and this is, you know, goes bigger and bigger now, and this you have in your notes, so you'll want to look over all that, but we don't have that much time left. I was thinking this was a nice, easy question. It's off an old exam, but you'll see right away this is very, very doable. Let's take a look. I think we can walk through this together pretty quickly. Use principles of molecular structure, IMF, and kinetic molecular theory to answer a complete Lewis electron dot diagram of the molecule ethyl methanoate is given. Identify the hybridization of the valence electrons in CW. So hybridization there, count your electron groups, and you have what? sp2 is correct. You have 1, 2, 3 electron groups. So that would be sp2. Estimate the numerical value of the HCXO right here.
No, it's the HY one.
Oh, okay, I'm sorry, it's the same one. So here. So look at this carbon. Shape with respect to that is? Shape with respect to that is? Tetrahedral.
Oh, I thought if you just counted.
No, because 4 things attached. So this is tetrahedral, and that bond angle is 109.5. Done. And there's wiggle room there.
We're not asking if you just had that molecule that they gave you in the question.
Yeah, no. You just want to focus on this angle here, but this C is still attached to those 4 things.
Oh, I see. It says in and F.
It's synthesized in the laboratory from ethanol and methanoic acid as represented. Now it says draw the complete Lewis electron dot diagram of methanoic acid. Methanoic acid is right here. And you could have done this in honors with ease, right?
It's just so much easier.
Cake. And I like this question too. Huh?
For the one before that, the bond angle, it said to explain your answer. What did you just say?
Did it say explain your answer?
It said give reasoning behind your, explain the basis of the rest.
Okay, so go ahead.
No, I'm just wondering, would you just be able to say because the shape's tetrahedral, or?
Mm-hmm.
Okay.
We'll double check that, but yeah, it's got tetrahedral molecular group geometry with a bond angle up. And this is a cute little question. In the box below, draw the complete Lewis electron diagrams of methanoic acid and a water molecule in an orientation that allows a hydrogen bond to form between them. Which hydrogen is capable of forming a hydrogen bond? You have to draw a water molecule. And where does my hydrogen bond go?
Right in between those.
Right there, right? Piece of cake.
Could they ask you to draw a dipole-to-dipole interaction between 2 molecules?
If they asked you to draw a dipole to dipole,
They would have to be the same molecule.
no. But it'd be easy if they were.
It's always dots.
It can be line, whatever you want. Just some sort of force. That's I wouldn't make a line because a line represents a bond. And it's really a shame that this is called a hydrogen bond because it really should be called a hydrogen force. I think it'd be easier for you. Yes, yes? Okay. Let me see what else we could take a look at. And this is off the 2014. This was the first year that they tried out the new exam. That just means it goes on, and it probably bothered the kids tremendously. There's like a whole bunch of these linkages.
Why are they talking about polymers?
Well, that's a whole separate issue, but let's just focus right here.
This is AP chemistry in high school. What?
It says PP is synthesized from propene and PVC is synthesized from vinyl chloride. The structures of the two molecules are below. And it doesn't really matter what's in the question. Just focus on what they're asking and your knowledge in terms of answering it. And you'll see it's not bad. The boiling point of liquid propene is lower than the boiling point of liquid vinyl chloride. Account for this difference in terms of the types and strengths of IMFs present in each liquid. So why would the boiling point of liquid vinyl chloride be greater than that of propene? Which molecule is polar covalent? Vinyl chloride. So propene has what IMFs? LDF only. Vinyl chloride has LDF and dipole to dipole. The fact that vinyl chloride has both, especially with stronger dipole to dipole, or dipole to dipole being stronger than LDF, gives rise to a higher boiling point. A higher temperature is required in order for the substance to go from liquid to gas. And again, the questions are just all over the place. This question's on density. This question is going to be on polarity and intermolecular forces.
Wait,
and
how would you do
A, it says a student places a mixture of plastic beads consisting of PP and PVC. Many of you, I'm sure, have heard of PVC piping, right? In a 1 liter beaker containing distilled water. After stirring the contents of the beaker vigorously, the student observes that the beads of one type of plastic sink to the bottom of the beaker and the beads of the other float. So what do you think they're talking about? Density. The chemical structures of the two are shown. Given the spacing between polymer chains is similar, the beads that sink are made up of which polymer?
confused. What do you do? How? If they don't give you anything but volume.
What is density equal to?
Mass divided by volume. They don't give you a mass.
Does Cl have a greater molar mass than CH3? Absolutely. 35 and a half versus about 12 and 3 is 15, right? So in this regard, clearly this density has to be greater, and based on the fact you had a 1 liter beaker for both, that's due to the fact of the greater molar mass of the chlorine compared to the methyl group,
You just
CH3.
have to assume that the beads are
What else
exactly
can you
one-
decide? What
one
else
mole of
could you
that.
do with it? Let's take a look on the guidelines on that one just to make sure, but yeah.
One mole.
And sometimes the questions are just, you almost think it's too easy. And the drawings on those questions really bothered the kids. Spot on right there, you had it. And then this one too.
It says propylene.
Yeah, but it doesn't. Or propene essentially nonpolar with only LDFs is the better answer. I don't know why they said that.
What do you mean essentially nonpolar? It is nonpolar.
It is nonpolar, I agree with you. It's a bad write-up on the guidelines.
It's essentially nonpolar.
All right? In terms of going over this, I would do some practice drawings. I would assess polar versus nonpolar. I would look at hybridization. I would make sure I understood IMFs and make sure your answers are clear. In terms of your practice quizzes and quizzes that correspond with this section, you should be looking at 2.2 and 2.3. And that'll help you in terms of getting more questions down. And again, best advice before your exam, call it a night by about 10:30 and get yourself ready. If you put the time in this weekend, you will be very successful on game day.